Welcome to the video lecture series of solid state devices. Course code EC301, contact hour 3 per week, credit 3. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department of Guru Nanak Institute of Technology, presenting this lecture today. This is Module 2, Junction Physics in Semiconductor Devices. In this module, there are actually three parts. First part is semiconductor junction, that is homojunction. And the first section is PN junction diode. So PN junction diode is nothing but the energy band diagram, creation of depletion region, plotting of junction voltage, depletion layer, and obviously the derivation of inbuilt potential, depletion width, junction capacitance, varactor diode, derivation of diode current equation, Zener breakdown principle, static and dynamic resistance, effect of temperature on breakdown voltage. So this lecture particularly emphasized to Zener breakdown principle, static and dynamic resistance of rectifier diode, dynamic resistance of Zener diode, effect of temperature on breakdown voltage. This is lecture 14. Moving to the next slide, let us start with introduction. A Zener diode is a particular type of diode that allows current to flow not only from its anode to its cathode, but also in the reverse direction when the so-called Zener voltage is increased. So Clarence Melvin Zener, the American physicist, invented the Zener diode. According to the name of the scientist, the name is Zener diode. So let us start with what is the Zener diode, what is the basic principle of Zener diode and all that. The Zener diode is basically a silicon PN junction diode. So silicon has been taken as it is abundant in nature. That's why the total fabrication technology has been shifted from germanium to silicon. Obviously, it is gradually shifted, not in one night or in 1 year, it has been shifted. The Zener diode is a silicon PN junction device that differs from the rectifier diode because it is designed for operation in the reverse bias voltage. And not only reverse bias voltage, in the reverse breakdown region. The breakdown voltage of a Zener diode is set by carefully controlling the level during manufacture. The basic function of Zener diode is to maintain a specific voltage across its terminal within given limits of line or load change. Typically, it is used to provide a stable reference voltage for use in power supplies and other equipment. This is the symbol of Zener diode. This is the symbol of Zener diode. This is positive side. This is negative side. And the straight line, what we use in case of normal PN junction diode, that will be a little bit broken at the end. So this is one of the number of 1N4740 is a germanium Zener diode. This is the input voltage. This is the very basic circuit that is shown here. The concept of resistance is we can't connect directly any device to the source. There must be a resistance. So moving to the next slide. Zener diode is designed to operate in reverse breakdown. Two types of reverse breakdown is there in a Zener diode, that is avalanche breakdown and Zener breakdown. Normally there is a concept that Zener breakdown always associated with Zener breakdown, but that is not true. There is also avalanche breakdown in a Zener diode. The avalanche breakdown occurs in both rectifiers and Zener diodes at a sufficiently high reverse voltage. So Zener breakdown occurs in a Zener diode at low reverse voltage. This point should be noted that avalanche breakdown occurs at Zener diode at high reverse voltage and Zener breakdown occurs at Zener diode at low reverse voltage. So a Zener diode is heavily doped to reduce the breakdown voltage, and this causes a very thin depletion region as it is heavily doped. The Zener diode's breakdown characteristics are determined by the doping process. So Zeners are commercially available with voltage breakdown of 1.8 volt to 200 volt. This range is from 1.8 volt to 200 volt. Any voltage can be taken as Zener breakdown depending on the specification of the diode. So this is the schematic of a Zener diode. This is P-type region, this is N-type region, this is depletion region, and this yellow portion is the junction. This is anode, this is cathode. So moving to our next slide. So working of Zener. This is the left hand side is showing the normal operating diode, that is normal PN junction diode, and the right hand side that is showing a Zener diode. What is the difference between these two? That is, see what is happening. Zener breakdown generally occurs at 6 to 10 volt. Beyond of that, avalanche breakdown occurs. So avalanche breakdown voltage is much higher than Zener breakdown voltage. Both are in third quadrant, as the current is positive but the voltage is negative, because avalanche breakdown and Zener breakdown, whatever may be, it always occurs in reverse bias voltage. So a Zener diode is much like a normal diode. The exception being is that it is placed in the circuit in reverse bias and operates in reverse breakdown condition. This typical characteristics curve illustrates the operating range of a Zener diode. Note that forward characteristics are not just like a normal PN junction diode. Look at the first quadrant of the diagram. It is just like normal PN junction diode. Beyond that, in third quadrant, we are getting the reverse breakdown region. Okay, so current is not much more, but the voltage is, current is maximum. Huge current is flowing through the device, through the diode, but voltage is less. So this is the breakdown characteristics. This breakdown characteristics shows us the reverse portion of a Zener diode characteristics curve as the reverse voltage VR, generally we take it as VR, is increased, the reverse current IR remains extremely small up to the knee of the curve. So this point is actually showing the knee. The reverse current is also called the Zener current, and it is denoted generally as IZ. So IZK is for knee current. IZT is the test current. If we want to test the Zener diode, then we should go up to this IZT, that is Zener test current. And at this point, the breakdown begins, and the internal Zener resistance, also called Zener impedance, begin to decrease as reverse current increases rapidly. It's showing that supporting the text that has been mentioned here. And IZM, M for maximum, Zener maximum current. So we are getting three currents, that is IZK, Zener knee current, IZT, Zener test current, and IZM, Zener maximum current. So Zener and avalanche effects are responsible for such a dramatic increase in the value of current at the breakdown voltage. If the impurity concentration is very high, then the width of the depletion region is very less. Obviously, now it is everybody knows this, that the depletion layer width is less if and only if the doping concentration of the diode is very high. Less width of depletion region will cause high intensity of electric field to develop in the depletion region at low voltages. Now, let's take an example to understand this clearly. Let's say the width of the depletion region is 200 ampere, very small. Sorry, 200 angstrom, very small. Angstrom means 10 to the power minus 10 meter. If a reverse bias voltage of just 4 volt is applied to the diode, then the electric field intensity would be 4 by 200 into 10 to the power minus 10. That is roughly coming that 2 into 10 to the power 8 volt per meter. That is the electric field, because electric field is the voltage by distance, and the distance is nothing but the distance of the depletion region. That's why we are getting the 4 volt by this distance of the depletion region, and we are getting the electric field that has been applied to the Zener diode. Now, merely a voltage of 4 volt is responsible to generate an electric field of intensity 2 into 10 to the power 8 volt per meter, very high intensity. And this electric field is sufficient to rupture the covalent bonds and separate the valence electrons from their respective nucleus. Large number of electrons get separated from their atoms, resulting in sudden increase in the value of reverse current. This explanation was given by scientist Zener. Such diodes are called Zener diodes. Zener effect predominates its diodes whose breakdown voltage is below 6 volt. Then after that we are getting actually avalanche effect. So this diagram shows that the presence of electric field, we can show that in across the depletion region, if the depletion region width is D and the voltage V is applied, then the electric field E has been developed across the depletion region. This field force on holes as well as this field force on electron. This is the N-type region, this is the P-type region. And y-axis showing the carrier concentration. We are not bothered about carrier concentration here because the P and N regions are heavily doped as it is a Zener diode, and we are only concerned about the electric field that has been applied across the depletion layer. So this is the construction of Zener diode. The Zener diode operation depends on heavily doped P-N junction diode. So the depletion region formed at the diode is very thin, less than 1 micrometer. So now even for a small reverse bias voltage of about 5 volt allows electrons to tunnel from the valence band of the p-type material to the conduction band of the n-type material. So Zener diode is highly doped or heavily doped. This is the main feature of Zener diode. Normal diodes also break down with a reverse voltage, but the voltage and sharpness of the needle are not as well defined as of a Zener diode. So Zener diode can be operated in breakdown region, and obviously in the forward bias condition it looks like a ordinary diode. So this is the graphical representation of IV characteristics of Zener diode. This is forward bias, this is reverse bias, and we are seeing that in reverse bias voltage, the voltage is current is maximum. Now resistance, in practice no diode is an ideal diode. This means neither it acts as a perfect conductor when forward biased, nor it acts as an insulator when it is reverse biased. In other words, an actual diode offers a very small resistance when forward biased and is called a forward resistance, whereas it offers a very high resistance when reverse biased and is called the reverse resistance. This is the practicality of the circuit or any device. We can't get ideal condition very easily. It is very tough. So we can take it as semi-ideal condition. So moving to our next slide, there are different type of resistance we are getting from diode. One is forward resistance, one is reverse resistance, and forward resistance can be classified as forward static forward resistance, static or DC forward resistance, and dynamic or DC reverse resistance. So what is DC forward resistance? Under the forward bias condition, the opposition offered by a diode to the forward current is known as forward resistance. The forward current flowing through a diode may be constant, that is direct current, or changing, that is alternating current. The forward resistance is classified as static forward resistance and dynamic forward resistance. So what is static forward resistance? The opposition offered by a diode to the direct current flowing under forward bias condition is known the forward DC forward resistance. It is measured by taking the ratio of DC voltage across the diode to the DC current flowing through it. So, if this is the forward resistance, it is clear from the graph that the operating point P, this point, the forward voltage is OA and the corresponding forward current is OB, and the static forward resistance is OA by OB. This is very simple diagram. Explain the condition of forward resistance or static resistance. So moving to the next slide. This is the dynamic or AC forward resistance. The opposition offered by a diode to the change in current flow I is called the AC forward resistance. It is measured by the ratio of change in voltage across the diode to the change in current through it. From the figure above, it is clear that for an operating point P, the AC forward resistance is determined by varying the forward current on both sides of the operating point actually and measuring the corresponding forward current DL. So it is showing that for the dynamic or AC forward resistance, the range generally 1 to 25 ohm, and it is not the ratio of constant voltage by constant current rather than the change in voltage by change in current. So now the point comes reverse resistance. What is reverse resistance? Under the reverse bias condition, the opposition offered by the diode to the reverse current is known as the reverse resistance. Ideally, the reverse current is infinite for a diode, but practically, as already mentioned, that it is not possible. However, in actual practice, the reverse resistance is not infinite because the diode conducts a small leakage current when it is reverse biased. The value of reverse resistance is very large as compared to forward resistance, and the ratio of reverse to forward resistance is 10 to the power 5 to 1 for silicon diode, whereas 4 into 10 to the power 4 to 1 for germanium diode. So reverse resistance for silicon is much higher than the germanium diode. This is one of the reason of using silicon diode instead of germanium. So now the effect of temperature on breakdown voltage. So let us start with temperature coefficient. So the temperature coefficient specifies the percentage change of Zener voltage for each degree centigrade change in temperature. For example, a 12-volt Zener diode with a positive temperature coefficient of 0.01% per degree Celsius will exhibit a 1.2 millivolt increase in Zener voltage when the junction temperature increases 1 degree centigrade. The formula for calculating the change in Zener voltage is del Vz equals to Vz into Tc into del T. Del T is nothing but the temperature change and Tc is nothing but the temperature coefficient, where Vz is the normal Zener voltage at 25 degree centigrade and the temperature coefficient is expressed as millivolt per degree centigrade. So del Vz equals to Tc into del T when we consider Vz equals to 1 volt. So this is an example here. So Vz is given 8.2 volt, temperature coefficient is given 0.0005 per degree centigrade and temperature rise is given 35 degree centigrade. If we put it in the formula, we are getting that the change in Zener voltage is 144 millivolt. So what is the actual voltage? That is Zener voltage at 60 degree centigrade. So Vz plus del Vz. That means 8.2 volt already is there. With that, for the temperature rise, we are in 144 millivolt is all additionally increasing. So if we add this to the net Zener voltage at 60 degree centigrade is 8.34 volt. So this is the application of Zener diode. This are used as a voltage regulator because already we have studied in our earlier lectures that how a voltage regulator can perform. Now Zener voltage, see when the breakdown is there, then if you increase the voltage, current will not increase, current is fixed, huge current is flowing through the Zener diode, thus it acts as a voltage regulator. As if the input voltage is increased, still the voltage across the Zener diode is not increasing, it is fixed, but the current is increased. So in this way, it acts as a voltage regulator in the breakdown region. It is already mentioned that voltage current falls below the maximum Iz value in the reverse breakdown voltage. So Zener diode can be used as a clipper also, because for positive half cycle, this Zener diode is forward bias. For negative half cycle, this Zener diode is forward bias. And when this diode is forward bias, this is short. We can't get that much of waveform across the output. Rest of the waveforms are going. Rest of the current for the rest of the waveforms are flowing through the circuit, and we are getting the clipped waveform. The positive half clipped a little bit and negative half also clipped little bit. So in this way we are getting the output voltage waveform. So the Zener diode acts as a clipper. Waveform clipper can be used not only reshape a signal but also to prevent voltage spikes from affecting circuits that are connected to the power supply. So in that sense, Zener diode is very much useful to suppress the spike or the damage of the circuit. So a Zener diode can be applied to a circuit with a resistor to act as a voltage shifter. Actually, it also acts as a voltage shifter because the voltage that has been developed across it, that is get added, and the resultant voltage is Vin plus Vz. So that's why it is actually acting as a voltage shifter. So another application is Zener diode is the it can cut the noise and by the virtue of its avalanche breakdown, and though another application of Zener is noise, use of noise caused by its avalanche breakdown in a random number. So this is one of the application of Zener diode. So this is the reading material, Donald and Millman Healthias. Any type of book can student can follow. If there is any question, please feel free to ask me this number, this email ID, shunipa.roy@gnit.ac.in. Thank you.